I wanted to make a video of the IEEE 754 notation, or the normalized notation from the book. It's basically what we went through in class, but this way you can have access to replay whatever parts you like. So we'll start off by talking about the IEEE 754 single precision floating point storage notation. That's how you find it on the internet. That's its official name. It just calls it normalized notation in the book. For 32 bits, there's three different parts. The sign, the biased exponent, and the mantissa are the significand. The sign is 1 bit, the biased exponent is 8 bits, and the mantissa is 23 bits. I wrote some steps down here to convert from decimal to the standard, the IEEE 754 standard. And so the top level 4 steps are: put the number in normalized binary notation, identify the sign bit, convert the exponent to a biased binary exponent, and then modify the binary mantissa. And then you take those three pieces, the sign bit, the biased exponent, and the modified mantissa, to get the three pieces of the IEEE 754 standard. So I got some more details in here on how you do that. I left the put the number in normalized binary notation steps out for this video. The second step, identify the sign bit. It's 0 for positive and 1 for negative. The third step is convert the exponent to a biased binary exponent. The way you do that is you take the exponent from the normalized binary notation and you add 127 to it. Then you take that resultant number and convert that to binary, and that will be the representation of the biased exponent that you store. The fourth step is to modify the binary mantissa. So the first thing you do is you remove that first one from the front of the mantissa, and then to get the 23 bits, you take the first part of the mantissa, if it's less than 23 bits, for the first part of the storage, and then you pad the rest with zeros. If there's more than 23 bits in your mantissa, like if you had a repeating digit for mantissa, you would just take the first 23 digits of that mantissa for storage. So if we were to take a look at the example here, converting 25 base 10 into the IEEE 754 standard, we'll go through those same steps we talked about before. We'll convert 25 base 10 to normalized binary notation, and that comes out as 1.1001 times 2 to the 4th. So we take that number 1.001 times 2 to the 4th, and we identify the sign. It's a positive number, so our sign bit will be 0. We'll convert our exponent to a biased binary exponent. The exponent is 4, so we'll add 127 to that. 127 plus 4 is 131, and then we'll convert 131 to binary to get our exponent. And then we'll modify the binary mantissa. So the mantissa is 1.1001. We'll truncate that first one off, and so we're left with 1001. We have to have 23 digits, so we have the first 4 there, so we'll pad the other 19 with zeros. So our final representation, you can see, is 0 for the sign bit. Then the exponent is 10000011 for the exponent, and then the mantissa is 1001 followed by 19 zeros. Let's take a look at a couple more examples. So the first one we show is the 1.1101 times 2 to the 9th, and so let's go through our steps. That is already in normalized binary notation, So we identify the sign bit. The sign will be 0. And then we convert the exponent to a biased binary exponent. So let's go through that. The exponent is a 9. We add 127 to that. 127 plus 9 is 136. And then we turn 136 into our binary number. You can see we have 8 bits. So the first bit will be a 1. That represents, so the place value for that is 127. So as we convert 136 to binary, we then take 136, subtract 128 from it, since we used 128 already. And that would leave us with 8. And so there would be a 0 in the 64th place value, a 0 in the 32 place value, a 0 in the 16 place value, a 1 in the 8th place, 0 in the 4, 0 in the 2, and 0 in the 1. So our binary exponent that we're going to store, or biased binary exponent that we're going to store, is 1 0 0 0 1 0 0 0. So then we look at our mantissa. That will be 1.1101. We'll modify that by removing the first one. That will leave us with a 1101. And then we'll pad the rest with zeros. So that means the number we're going to store will be 0 1 0 0 0 1 0 0 0, and then 1101 with 19 zeros after it. Let's take a look at one more problem. And this one's in binary notation already also. It is 1.001 times 2 to the first. So let's go through our steps here again. The number's already in binary notation. We identify the sign bit. And it's a positive number, so we use 0 for the sign bit. We'll convert the exponent to a biased binary exponent. Our exponent is 1. We'll add 127 to that. That's 128. That's a little bit easier number to convert because we put a 1 in the 128 place value place, and then it's followed by 7 zeros. Then we modify our mantissa. The mantissa is 1.001. We chop that first 1 off, and we're left with 001. And then we truncate we fill in the rest with 20 zeros to get our 23 bits. So that means our IEEE 754 standard notation will be 0, and then a 1 followed by 7 zeros, and then 001 followed by 23, or excuse me, a 001 followed by 20 zeros. So I recommend going through this video again. As we go through the problems, pause the video and then see if you can work them out on your own, and then let the video play and see if I worked them out the same way you did and got the same answer that you did.